Okay, welcome to another chemistry tutorial video. Here we'll be proceeding to Charles' law. We've actually examined Boyle's law. Here we're just going to describe Charles' law quite briefly. Let me just state it simply. Charles' law essentially states that the volume of a fixed mass of gas is directly proportional to the temperature, provided that the pressure remains constant. Logically, when you heat an object, it expands, its volume increases as you keep heating it. So adding heat is increasing temperature. And increasing temperature expands the object. So it's expected that a gas should actually increase in size if heat is added. And it's expected that a gas should actually shrink if heat is being withdrawn per se. These laws basically are for ideal gases. They have not really been truthful when it comes to real gases, but they make a lot of our calculations easier and they make us able to do quick rough estimates and quick predictions about the behavior of gases in particular. And owing to the fact that gases have overcome intermolecular forces of attraction, it makes these laws more suitable for them and it makes their behavior even more predictable since several factors are not taken into account because they are not thoroughly involved, so to speak. So if you do the plot of the Charles law, a volume versus temperature graph, you're going to get a straight line that goes in that particular format. That is if you're actually plotting it volume versus temperature, absolute temperature in Kelvin. If it is volume versus absolute temperature versus temperature in Celsius, you're going to have a graph that goes more or less like this, where this is going to be negative 273.16 degrees Celsius. You're going to have a graph of this particular format, so to speak. You're going to have a graph of this particular format, so to speak. So the general statement of the Charles law is that volume is directly proportional to temperature. So it can be shown that V1 over T1 is equal to V2 over T2. Essentially, the relationship there can easily be proven. And once a relationship like that can easily be proven, you can actually use it to be able to solve lots of problems. So let's do an example to show us what happens when we change or run some quick transformations. First and foremost, okay, solution. Our initial volume is 15 dm cube. Our initial temperature T is 27 degrees Celsius. The first thing we need to do is to convert it to Kelvin, so we simply add a 273 to that, and that will give us a 300 Kelvin. Now that we're actually taking care and taking note of that. The volume, we're to find the volume when the temperature is tripled, so to speak. So V1 over T1 equals to V2 over T2. So we have to find the volume when the temperature is tripled. That means we have to find V2. V2 is just going to be V1 over T1 times T2. So that implies that V2 essentially will be 15 all over T1, which is 300 times T2. T2 is triple of T1. So triple of this, that's 3 times 300 is 900. Well, essentially this goes into this, that's 315 times 3. The volume also triples as well, as we can see. That's for the A part. For the B part, the temperature when the volume is tripled, essentially T2, we'll make T2 so the formula T2 is just going to be V2 times T1 over V1. And basically, V2 is triple of T1, which is going to be 45 times T1, which is 300 over this, which is, so if we actually do the multiplication for that, we get 900 Kelvin. Okay, so if you triple the volume, you triple the temperature as well. If you triple the temperature, you triple the volume. And if you keep doing that, so you double the temperature, doubles the volume. Tripling the temperature, triples the volume. Multiplying the temperature by a factor of halving the temperature is halving the volume. It's as simple and as straightforward as that. Thank you for watching.